Okay, so in this section, 4.4, we're going to talk about something called an imaginary number. And basically three things we want to know. What is an imaginary number? How do you raise imaginary numbers to different exponents or different powers? And then how do you do the four basic math operations, adding, subtracting, multiplying, dividing, with imaginary, or what we can also call complex numbers. And we'll explain that a little bit more later on. First of all, the imaginary number is this right here. So if I said, for example, what is the square root of 1, you would probably be able to tell me that 1 is the answer. 1 times 1, 1 squared equals 1. There's actually another answer, though. You could also say that negative 1 is the square root, because if you square a negative 1 times negative 1 is also 1. Now, on the other hand, if I said this, if I said what's the square root of negative 1, there is no number, there's no real number that you could make that happen with. Negative 1 squared is still positive 1, and positive 1 squared is positive 1. There's nothing that you can square to get a negative number. So to get around that, mathematicians say, okay, since there's no real number that we can do this with, let's just call that I, which stands for the imaginary number. So what is I? What is the imaginary number? It's just defined to mean the square root of negative 1. That's what I means. Okay, what's interesting though is suppose that now we take I and we square it. If we square it, well, that means I squared is going to be this right here. If you square root something and then you square it, they cancel each other out, and you're just left with negative 1. And why is that interesting? Because we started with an imaginary number. We started with I, and yet when we square it, now we have a real number. Now we have negative 1. Okay, so that's kind of an interesting fact, that you can move from a world of imaginary numbers to the world of real numbers. Okay, so what we want to do now is learn how to simplify imaginary numbers and then raise them to different powers. Okay, so what that means when we come to simplifying, suppose for example we had this. Suppose we had the square root of negative 9. Well, I could write the square root of negative 9 as the square root of negative 1 times 9. We now have a name for this. We have a name for the square root of negative 1. It's called I. And we know that the square root of 9 is 3. So I times 3, or 3i. That's what the square root of negative 9 equals. Okay, so we'll talk about how to simplify square roots now. Unfortunately, they're not always nice even numbers like 9. They might be something like 18 or something that's not a perfect square. So we'll show you how to do that. First of all, what are the perfect squares? They're those numbers in red that you see listed here. They're numbers that you get when you take a number and you multiply it by itself. Okay, so those are the squares, those red numbers. And when you're factoring perfect squares, when you're simplifying what are called radicals, radicals is a word for square root, you want to look for 4 of these especially. The 4 easiest ones to factor are this one 4, this one 9, this one 25, and this one 100. So it's always easiest to look for those first. Okay, these 4 right here. And I'll show you why. There's basically some tricks for telling if a number goes into that. Let's start with 100. The easiest way to tell if a number can be divided by 100 is if it ends in double zero. So this huge number right here, because it ends in double zero, can be divided by 100. So I could write that as 100 times 7,896. What about 25? 25, I tell people to think of quarters. These numbers here, that's 1 quarter, 2 quarters of money, 3 quarters of money, 4 quarters. So if it ends, for example, in 50 or 75 or 25 or double zero, that means that number can be divided by 25. 25 is a perfect square. That's why we're doing this. We're looking for perfect squares. All 4 of those numbers, 4, 9, 25, and 100 are perfect squares. What's the trick for 9? The trick for 9 is to take the digits of a number and add them together, which you see right here. And because those add to 18, we ask ourselves, is 18 divisible by 9? It is. So that means the original number, 72,081, is also divisible by 9. And the last thing, for 4, you look at the last 2 digits. So this huge number here, we only need to look at the 44. Since 4 goes into the number 44, it also goes into that number right there. Okay, I think it goes in, I want to say 46,561 times evenly. Yeah, how did I know? I just looked at those last 2 digits. So let's simplify some of these. So here's our perfect squares. I'll list them right here. And we're looking for numbers. We're looking for a way to factor those out, I should say, to be able to simplify those. Usually if you go to 10 squared or 12 squared, you're set. So the very first thing we do when we have negative square roots is we pull out a square root -1, which equals I. And now if you look at root 27, if you look at this list, what's a perfect square that divides evenly into 27? Well, obviously 36 is too big. We would start at 25 and just count backwards. 25 doesn't work, 16 doesn't work, but 9 does. Okay, 9 turns out to be, or 27 turns out to be 9 times 3. The square root of 9 times square root of 3 is 27. What is the square root of 9? It's 3. I can't do anything more with square root of 3, and then I still have that I. The traditional way of writing this is you write that number outside the square root first, then you write the I, then last comes the square root. So this right here is the simplified version, 3i root 3, or 3i radical 3. That's the simplified version of square root -27. Alright, let's try 216. Again, the first thing I want to do is I want to pull out a square root -1, which is also known as I. And then, well, 144 doesn't go into 216, neither does that, neither does that. That doesn't work, that doesn't work, that doesn't work. This one does go into 216. Okay, 216, by the way, if you add 2 plus 1 plus 6, you get 9, so that means 9 goes into it. And you also, if you look at the last two digits, 4 goes into those, so that means 4 and 9 go into it. Well, 36 happens to be 4 times 9, so 36 goes into it 6 times. 216 is root 216 is root 36 times root 6. Root 36 equals 6. I can't do anything more with the root 6. You could break down 6 into root 3 times root 2, but neither root 3 or root 2 are on this list right here, so that's not going to help us at all. And then my final answer would be 6 times I times root 6. We normally write the number in front, then the I, then the square root. Okay, here's kind of an interesting pattern. I to the first, you can see up there, it just equals I. I squared, we said that I squared is the same as the square root of -1, because that's what I is, squared. And squaring and square rooting cancel each other, so we just get -1. Okay, I to the third can be written as I squared times I to the first. If you remember from earlier kind of algebra studies, you add these exponents to get that number. So I squared, we already said that that's -1, and we already said I to the first is I. -1 times I is just -I. Okay, I to the fourth is the same as I squared times I squared, because 2 plus 2 is 4. And we know that I squared times I squared, well, I squared is the same as -1, so that's like -1 times -1, which is 1. Okay, so here's the thing, you have this kind of 4 numbers up here. We want to see, is there like any pattern here? Does it just keep doing different things, or there's some kind of regular repeating pattern that shows up? And you're about to see there is a pattern. I to the fifth can be written as I to the fourth times I to the first, and we just found I to the fourth down here. I to the fourth is 1, so that's the same as 1 times I, which is just I. Okay, I to the sixth is the same as I to the fourth times I squared. I to the fourth we already said is 1, and I squared is right here. 1 times -1, so that's -1. I to the seventh is the same as I to the fourth times I to the third, which is 1 times I to the third is -I. So 1 times -I is -I. And then finally I to the eighth is like I to the fourth times I to the fourth, which is 1 times 1. Okay, so here's what you may notice. We have this pattern. I to the first, down the line it goes I, -1, -I, and 1. And then down here, I, -1, -I, 1. So the pattern is that this pattern, or this kind of I, -1, -I, 1 pattern, it repeats every 4 exponents. So how is that useful to us? Well, if we had a huge number, let's say we had like I to the 86,234, okay, there's 2 ways you can do this. The painful way to do it would be to count out patterns of 4 till you get all the way to 86,234, but there's a much easier way. Take this number here, divide it by 4. Okay, and really remember, dividing by 4, we just have to look at the last 2 digits. So we're really doing 34 divided by 4. 4 goes into 34 8 times, and it gives you a remainder of 2. And that remainder is going to tell you which of these 4 it falls into. If it has a remainder of 1, it's going to equal I to the 1. If it has a remainder of 2, it's going to be I to the 2, which is, you can see in that table, it's negative 1. If it has a remainder of 3, it's going to be like I to the 3, which is negative I. And then finally, if it has no remainder at all, it's going to be like I to the 4th, because 4 divided by itself has no remainder. And I to the 4th up there is 1. So that's the pattern. You take any number at all, you divide it by 4, and it's going to be one of these 4 remainders, which means it's going to be one of those 4 values up there, either I to the 1st, I to the 2nd, I to the 3rd, or I to the 4th. Those are the only possibilities. Okay, before we do a little bit more practice of that, let's try each of these. So these are multiplying numbers together. Negative 5 times 3 is negative 15. I times I is I squared. Remember before that we said that because I equals the square root of negative 1, when you square it, these are going to cancel and you're just left with I squared equaling negative 1. So negative 15 times I squared, that's the same as negative 15 times negative 1, which is just positive 15. Okay, what if you have to multiply two negative square roots? What you can't do is you can't start just doing negative 6 times negative 15. You can do that for real numbers. These are not real numbers though, these are imaginary numbers. So the first thing we always do when we have negative square roots is we first start by pulling out a square root of negative 1. We're pulling out an I. Okay, so we have what you see right there. Now we can do I times I, which is I squared. And remember that's negative 1. And we have root 6 times root 15. 6 times 15 is 90. And now we're at the point where we were before. We can look for perfect squares to pull out of that. So if you look at 90, let's go up to 8 squared here. Okay, if you look at 90, 90 has this number that goes into it. So 90 can be written as 9 times 10. Root 9 times root 10 would be root 90. And what is the square root of 9? That's equal to 3. Can't do anything more with 10. It is 5 times 2, but neither 5 or 2 are perfect squares. So your final answer would be negative 1 times 3, which is negative 3, times radical 10, or times root 10. That's the simplified version of radical negative 6 times radical negative 15. Alright, let's do a couple more of these. So 3I times 4I. 3 times 4 is 12. I times I is I squared. We already said I squared is this number. So the final answer should be negative 12. Right here, root negative 20 should be broken into root 20 times root negative 1. Root negative 12 should be root 12 times negative 1. Okay, these are both i's right here. And then root 12 and root 20, they both have perfect squares in them. Here again are the perfect squares. You look at 20, you don't need to go past 25 for either of those. 20 is the same as 4 times 5. And 12 is the same as 4 times 3. So root 4 is 2. Can't do anything with the root 5. I times I is the same as I squared. Root 4 is just 2, and root 3 is still there. 2 times 2 is 4, so we still have that I squared there. And then root 5 times root 3 is root 15. Only one more thing we can do. I squared is the same as negative 1, so that's like 4 times negative 1, which is negative 4, and then we still have the root 15. Okay, last one for this section, I to the 31. We need to take the number 31 and divide it by 4 because the pattern repeats, if you remember, every 4. Here's the pattern again. I squared is negative 1. I to the third is negative I to the fourth is positive 1. So it's going to have to be one of those 4. 4 goes into 31 7 times with a remainder of 3. And because it has a remainder of 3, it means that that is going to equal the same thing as I to the 3, which means it's going to be negative I. Okay, now that we know what imaginary numbers are, we can use them to solve equations that we couldn't previously solve. So if you had to solve this equation here, you would start by subtracting 64. That means x squared equals this. We need to square root both sides and put a plus or minus in front. So the square root of 64 will negative 64, that's the same as 64 times negative 1. Square root of 64 is 8. Square root of negative 1 is I. So that's the same as plus or minus 8i, and that's the solution. There's no real solution to that. It just has an imaginary solution. Let's do this one. Divide by 100, subtract 100 from both sides. You get 4x squared equals negative 100. And we'll divide by 4. So x squared is negative 25. To cancel out the squared, we need to square root. and we put a plus or minus in front. So x equals plus or minus, again, square root of negative 25 is like 25 times negative 1. That number is 5, and another name for square root of negative 1 is I. So the solution to this equation is positive or negative 5i. Okay, what is a complex number? Complex doesn't mean complicated, it means a combination. It means a combination of a real part, like 5 for example, and an imaginary part like 2i. So every number actually is a complex number. The number 8 can be written, it would be strange to write it this way, but you can write it as 8 plus 0i. There's no imaginary part. Okay, 17 would be 17 plus 0i. The imaginary numbers that we did, so on the last page we wrote 5i, that's the same as 0 plus 5i. This is the real part right here, and this is the imaginary part. That's what a complex number means. So let's look at this. We have this complex number, and we want it to match up with this. So if you look at it, the real part of this, let's do the imaginary part first actually. The imaginary part of this number is 6, and the imaginary part of this number is y minus 3. So if we solve that for y, we would get y equals 9. If you took 9 and you plugged it in right here, you get 9 minus 3, which is 6. Okay, how about the real part? The real part of this number is 7, and the real part of this number is 3x minus 5. So let's solve that by adding 5 to both sides. You would get 12 equals to 3x, which means x equals 4. And that's the solution that when I plug it in here would give me 7 right there. Okay, last things, the 4 basic math operations: adding, subtracting, multiplying, dividing. Let's just do subtracting. That will cover adding as well. So when you have a minus in front of a parentheses, you need to distribute it. That becomes minus 3. Minus 6 is like plus 6. And now we have 4 minus 3, which is 1. Negative 8i plus 6i would be negative 2i. And that's all you need to do. You're done. Okay. How do you multiply things? So this is an example of a real-world situation where you use imaginary numbers. They use it in electricity. It models something called impedance. And in this equation, the J, I believe, stands for joules. The J actually means I, like the I that we were just using. So this equation right here, that's the equation for voltage. Voltage equals the current times what's called the impedance, current that the electricity runs. They're telling us here that the current is 2 plus 4i. Remember, I means the same as that J that they originally had. And they're telling us that the impedance is 9 minus 3i. So you may recognize this. What this looks like is it looks like we have to FOIL this out. And that's exactly what we have to do. FOIL means first outside, inside last. So first terms here would be 2 times 9, which is 18. The outside terms would be 2 times minus 3i, which is minus 6i. The inside terms would be 4i times 9, which is plus 36i. And the last terms would be 4i times negative 3i. 4 times negative 3 is negative 12, and I times I is I squared. So let's simplify this. We have 18, well remember I squared is the same as negative 1, so that's like minus 12 times negative 1, which is positive 12. So we have 18 plus 12, that's 30. That's the real part of the number. And we have negative 6i plus 36i. Negative 6 plus 36 is positive 30. So this is our final answer. It has a real part 30 and an imaginary part 30i. Okay, the last example is dividing, and to divide you need something called the conjugate, or the complex conjugate. So here's what that means. I'll give you a couple examples here. Let's do this one, and let's do one more. Let's do 1 minus 12i. Let's make that 7 minus 12i. So each of those are imaginary or complex numbers. In the other table I'm going to write the conjugate. The only thing you have to do to find the conjugate, all you need to do is you just need to change this middle sign right here. Everything else stays the same. So the conjugate of 3 plus 4i is 3 minus 4i. Conjugate of negative 2 minus 8i is negative 2 plus 8i. Conjugate of negative 1 plus 10i is negative 1 minus 10i. And the conjugate of 7 minus 12i is 7 plus 12i. Why do we care about this? Why do we need to use this? because when you multiply these together and you FOIL them, it will cause the middle term to disappear. You might remember this from factoring. If you had to factor, let's say this, that's called a difference of squares. It turns out to be x plus 3, x minus 3. And notice the pattern. The pattern is that one of these is plus that number, one of them is minus that number. That's the same pattern here. One of them is plus, one minus. One of them is plus, one of them is minus. When you FOIL it, you can see that there's no middle term here. It just goes straight from x squared to the number. And that will be useful to us when we do these problems. So the rule for simplifying, when it says simplify, the rule is that you can't have any i's on the bottom. To get rid of them, you multiply the top and bottom by the conjugate. And remember, the conjugate is just this sign reversed. So 3 plus 6i, its conjugate is 3 minus 6i. This one, the conjugate of 5i, would be negative 5i. And this one down here, the conjugate of 1 minus i, would be 1 plus i. Okay, what will happen if we do this correctly is the I should now disappear when we FOIL it. So let's try that. So 3 times 3, we're FOILing the bottom, would be 9. 3 times negative 6i would be minus 18i. 6i times 3 would be plus 18i. And again, here's what happens. They cancel each other. They disappear. And then 6i times negative 6i would be negative 36. I times I is I squared. So that's like negative 36 times, remember, I squared is negative 1. So negative 36 times negative 1 is plus 36. Okay, what is the top? Well, the top is 2i times 3, which is 6i, and 2i times negative 6i is negative 12i squared. That's the same as minus 12 times I squared is negative 1. So minus 12 times negative 1 is plus 12. So the top is 6i plus 12. And the bottom is the 9 plus the 36, which is 45. And then what you can do, just to make this a little bit easier, a little bit simplified more, is you can split this down the middle and put both of them over 45. That's going to be plus, that's supposed to be 6i. Okay, both of these are divisible by 3, so 3 goes into that 2 times, and it goes into that 15 times. 3 goes into that 4 times, it goes into that 15 times. Your final answer would be 4 over 15. Plus, that's 2i over 15. That is a simplified version. Notice that the bottom only has 15. It doesn't have any i's in it. Okay, and then we'll finish up with this one. So this needs to be FOILed again if we do the bottom correctly. By the way, I forgot to mention that you have to multiply the top and bottom by this, because 1 plus I over 1 plus I, that equals 1. The question is, what happens when you multiply something by 1? Nothing happens. It stays the exact same. Any number times 1 equals itself. So that's why we're allowed to do that. If you FOIL the bottom, 1 times 1 is 1. 1 times I is I. Negative I times 1 is negative I, and those cancel, which is what we wanted. Negative I times I would be negative I squared, which is negative 1. So that whole thing becomes plus 1. So we have that 1 plus that 1 equals 2. Now the top, 2 times 1 is 2. 2 times I is 2i. I times 1 is I. Remember, it doesn't matter if the i's cancel from the top, we only care about the bottom. And then I times I is I squared. I squared is negative 1. So 2 minus 1 would be 1. 2i plus I is 3i. And that's as simple as you can get. So we learned today about imaginary numbers. I is the square root of negative 1. And how to add, subtract, multiply, divide them, how to raise them to powers, that pattern that repeats every 4. And that is section 4.4.